finish any class, so I finished.
Last kind of, because like last year, weren't they had like a theory that he was gay with his lab assistant, and I thought that was
What?
funny. I don't know, that would have made for an interesting discussion.
Shifting gears.
I thought you were switching lanes.
Okay, so
Trust
so
me, I play
here's,
racing games.
Oh my god.
here's kind of a fundamental problem that people faced prior to the development of calculus. This was one of the driving factors in why Newton and Leibniz came up with this idea of the calculus. So what if we wanted to find, it's easy to find an average rate of change, right? Average rate of change is no big deal. That's just the slope of a secant line connecting 2 points, right? So for example, if we've got a point here at, let's call this, what's the book call it? I want to make sure I use the same, because there's a million ways to write this. Let's see, I want to use x and delta x probably, I'm guessing. First time through, I can't remember. Can't find my notes, that's all right. Yeah, we'll do that. So, let's call this x, and let's call this x plus delta x. Okay. And if we want to find the average rate of change, well, that's no big deal, because the coordinates, if this function is f, right, then what are the coordinates at that point right there? X, f of x. So we'll call that f of x. And if this is x plus delta x, what are the coordinates going to be there? X plus delta x. F of x. X plus delta x, right? Okay. And here's f of x plus delta x. Finding the slope of the secant line is no big deal. All right, that's just an average rate of change, and it just looks like something kind of like, I kind of missed the there, close enough, right? Okay. So there's, if I want to calculate the slope of the secant line, it's just a slope triangle, right? So we just end up with my rise, which is the difference in those y values. Everybody agree? So
F delta plus delta x minus f x.
right? Okay. And the run is just what?
Delta x.
Delta x. Everybody agree? Okay. Good. That's the slope of the secant line. It's an average rate of change. But that's not always the quantity that we're looking for, right? Like if we're talking about, for example, we want to find out what our average speed is between here and Hermiston, then that's great. We just take the total distance divided by the total time and get the average speed, average rate of change. No big deal. But if we want to know what the instantaneous speed is, that's not really what we're looking for, right? What are we looking for? If I want to know, for example, what is the instantaneous speed right there, what kind of line do you suppose I'd be looking for?
By instantaneous speed, you
I mean, I
Speed
wanna
in
know
any
what
one
the-
single point.
what the speedometer would say at that point, right? What kind of line? Secant is a line that connects the curve
Tangent.
into, it's tangent line,
mean,
right?
she said.
Okay, tangent line. Yeah, tangent line. Tangent line is what we want, because a tangent line by definition is the line that just touches the curve at that one spot locally. I mean, it might hit it somewhere else if the curve dips down. We don't, that's sort of extraneous, right? We don't care about that. But in the region of that one value of x, the tangent line is the line that touches the curve in one place. And as we zoom in on the curve, closer and closer and closer, and the curvature disappears, the tangent line would be seen to coincide with the curve. Everybody see what I'm saying? If I were to zoom in and zoom in and zoom in, that blue curvature is gonna appear to flatten out. It's gonna start to look like the tangent line, right? Everybody see that? Okay? So how are we gonna get that though? Right, that's the trick. I mean, that's what people were faced with, was how do you do that mathematically? We can see what we want as the tangent line, but how are we gonna come up with that analytically? Now, what if we wanted to know the speed at which we're traveling by Rue Elevator between here and Hermiston? If I just measure the whole distance from here to Hermiston divided by the time it takes to get there, it's not very accurate. How could I use that same concept to maybe get a more accurate prediction? What could I do? Well, okay, that's what we're gonna do, right? That's what we're gonna do. But say if we're just gonna use an average, gonna take a distance over a time. What could I do to get maybe a more accurate estimate of what's happening right when I go by Rue Elevator than taking the whole trip?
Do you have the function of your speed?
No, but even in my car, if I just want to get a more accurate
Oh, you look at
estimate. Well, so much ground was broken.
Just fucking, yeah.
Would you shorten the time?
I could shorten the time, right? Everybody agree? I could shorten the time up. Instead of doing the whole trip, what if I just did like a mile around Rue Elevator? That's gonna be much more accurate, isn't it? And if I want to get even more accurate, I could shorten it up more than that, right? I could just mark off like 100 meters on the side of the road and time how long it takes me to go by 100 meters, right? The smaller the increment, the more accurate it's gonna be, right?
On
Okay.
paper.
Well, no, in reality, it's gonna be more accurate. The shorter the interval.
Okay, yeah, never mind.
You get the idea?
Yeah.
Okay, so how can I mean, that sounds like a great process, but is there a way that I could take that process to its extreme? Like I could maybe take it to its limit, that process?
Go as far as you
What could I do? Like I could apply the same idea to this curve, couldn't I? I could get a more accurate secant line by doing what?
Just finding the average of the shorter time you're.
I'm taking a shorter interval, right? So what if I were to drag this point back further this way? So I make delta x smaller. Everybody agree that if delta x is smaller, let's say I put delta x over there instead. Well, now that secant line is starting to look more like the green tangent line, right? And to get it even more accurate, I'll bring it closer. How could I get it infinitely accurate? I could take the limit as what goes to zero. As what? Delta x, yeah, right? We could take the limit of the slope of the secant line as delta x approaches zero, right? And that should give us an exact answer then. Everybody agree? Okay, so what is the slope of, isn't that cool? That's a great strategy. So what is the slope of a secant line? Just rise over run. Well, there's my rise and there's my run, right? So it's f of x plus delta x minus f of x over delta x, right? Okay, everybody agree? Just rise over run. That's our slope triangle. If I want to calculate the slope of a tangent, the slope of the tangent line is really just the limit of the slope of the secant line as delta x goes to zero, right? So it's going to be the limit of f of x plus delta x minus f of x over delta x. That's delta x goes to zero. So if I directly evaluate, what's obviously going to happen here? 0 over 0, right? Okay, it's indeterminate. So I'm going to have to do some algebra magic
How
here.
would f of x be 0?
as delta x goes to, x is not the variable of the limit. But if delta x goes to 0, I just get f of x minus f of x over 0, which is 0 over 0, right?
Yeah, oh, yeah.
Okay, but that's a great trick. That is what we call the derivative function. Okay, that's what a derivative does. A derivative, its job is to tell us the instantaneous rate of change of a function. So in other words, graphically, it tells us the slope of the tangent to the curve at whatever input. Right? So let's try this now. Let's do this for let's do this for a certain function. So let's do this for how about
So the point of this is to find essentially what one single point is on a function, right?
to find what the slope of the tangent to the curve is at one particular point.
What's the advantage of knowing the slope of the tangent curve?
Because that's something that's valuable to know. What if I want to know, that's an instantaneous rate of change, right? So for example, if I were to graph, well, say I'm just going to graph position versus time. So let's say this is position, call it v as a function of time, and this is my curve. And I want to know how fast we're going at that value of time, right there. Well, that's going to be the slope of that tangent line. Okay? So we're going to come up with a way to find that instantaneous rate of change. Okay? There was, before calculus, there was no way to do it. There was no way to find the slope of that tangent line.
So somebody just made it up or they figured it out?
They figured it out. Yeah, they figured it out. This is what calculus does. Calculus does, you'll kind of get an appreciation for what calculus does to everything you've done in the past. It just makes it way, way better. In the past, you could do things, like we could find average rates of change. Sure, that's okay. I mean, that's what we do in our physics class. It's not a calculus-based physics class. But it's way better to be able to find, additionally, instantaneous rates of change, right? Before we could calculate, and we'll see this in the near future, we could calculate static things, like we could calculate a volume of a sphere, like a spherical balloon. With calculus, we can calculate the rate of change of the volume as a function of time. We can see how fast the volume is increasing, or how fast the radius is increasing when we pump air into it, things like that. It takes static stuff and makes it dynamic. Right? Once you've done calculus, you just realize how kind of limited you were before. So this is our goal, right? So let's take an example. Let's just take a specific curve. Let's take something. We'll take a couple. Let's start off with a real simple one, and then we'll get a little more complex. Okay, so let's take the function. How about f of x equals 2x minus 3, and let's go ahead and find the slope of the tangent to the curve at the point x equals 2, and what would that make y? 1. Okay? Everybody see? All right, so we're going to start with, we know that the slope of a tangent is just the limit of the slope of the secant, right? Okay, so our newfound, they show you that in this section. Yeah, they do. Okay, so our newfound name for that is the derivative. Okay, so we'll call that, but for now I'm just going to call it the slope of the tangent equals then the limit of f of x plus delta x. We always start with this definition. This is our broad general template, and then we'll get specific based on whatever problem we're doing. Okay. This is the definition of the slope of any tangent line.
And it's always gonna approach 0?
Yep. Yep, exactly. So we're letting that space approach 0. So essentially then, we're just taking these 2 points that define the secant line, and we're migrating one of them back so that they just meld together into one point. Okay? So there's our template. Now, what have we got here? So we know some other stuff. We know that for us, here's our function, right? Everybody agree? And we even know the x value, right? We know that the x value is even 2, okay? So let's put in the function first, okay, and we end up getting the limit of what's f of x plus delta x, if that's f of x. What are we gonna get? So if f of x is 2x minus 3, what's f of a? F of x is 2x minus 3, what's f of a? 2a minus 3, what's f of b? What's f of the quantity x plus delta x? 2 times the quantity x plus delta x, plus minus 3, right? Okay. So we get the limit of 2 times x plus delta x minus 3 minus f of x is 2x minus 3, right?
So did the x just become x plus delta x?
Yeah. Divided by delta x as delta x goes to 0. We could even be more specific because we know that the x value we're choosing is 2, right? So I could even replace all the x's with 2's if I want, right? Okay, so if I do that, that becomes a 2, that becomes a 2, and we should be able to simplify this and get an answer now. If I just directly evaluate, I get 0 over 0, right? But we know how this stuff works. If I get 0 over 0, when I take this limit, if I simplify the limit, I know that I'm going to eventually be able to cancel out the delta x's and get an answer, right? So what happens if I do the simplification? What do I get in the top?
4, 1 minus.
So 4 plus
2 delta x
minus 3 minus what?
1.
4, okay, 4 minus 3, okay, same thing. So that's, what do we get then? 4 minus 3 is 1 minus 1. So does everybody agree that all that stuff cancels out on the top? Okay, and what's our answer then? Okay, right, so I end up with the limit of 2 delta, well, not delta x. I end up with the limit of 2 delta x over delta x. As delta x approaches 0, what can I do? Algebraically. Cancel, right? So I can just do that, and so I get 2. So at x equals 2, we got a slope of 2. Is that a surprise to us, based on what that function was? What is that function that we started with? What is that? It's a line with a y-intercept of -3 and a slope of, okay, so big deal, calculus didn't help us much there. We already knew what the slope was, right? Okay, well, let's pick one that we don't know what the slope is, okay? So let's try maybe, how about a quadratic or something? Let's do a cubic.
Turn it up to 11.
Turn it up to 11. Your amplifier's good at 11?
Yeah. Yours don't?
Of course we do. We'll do a quadratic. We'll work our way up. We'll just do that, how about, okay? And let's find the slope of the function at the point x equals 1. So what's y equal? So at that point, we want to find the slope of the tangent line, right? Okay, so then f prime of 1, I guess we haven't used that notation yet, so we're just calculating. We'll get into that in a second. So we're calculating the slope of the tangent at x equals 1. So that's equal to, you tell me. I'm going to start off with what's my broad template? What's the definition of the slope of the tangent line?
The f, parentheses, x plus delta x minus f of x over delta.
As delta x goes to 0. Good, okay, so then we've got our x is a 1, right? And our function is x squared plus 3, right? So what does this become then? So this part right here becomes, what's f of x is x squared plus 3, what's f of hand? What's the pattern? F of x is x squared plus 3. F of 9 would be 9 squared plus 3. F of a is a squared plus 3. What's f of hand?
So x.
Hand
Hand squared plus 3, right? So hand is just the quantity 1 plus delta x. Everybody agree that's f of 1 plus delta x? Right? Minus f of 1 is just 1 squared plus 3. Divided by delta x as delta x goes to 0, right? Okay. So what's that give us? If I square this out, I'm going to get the limit of, what's the quantity 1 plus delta x squared? 1 plus 2 delta x plus delta x squared plus 3 minus 1 plus 3 is 4. Okay. All divided by delta x. Delta x goes to 0. Let's see if we can cancel anything horizontally. Does anything add to 0 here? Well, 1 plus 3 is 4 minus 4. Okay, so all the naked terms go away, right? Every term we're left with has a factor, at least one factor of delta x in it, right? So what can I do to all those terms right there? Factor out of delta x. What am I left with on the top if I
2
factor
plus
out of
delta
delta
x.
x? So I'm going to get 2 plus, I'm taking one of those away, so I'm left with a delta x divided by delta x. As delta x goes to 0, then look what happens. Right? Look what happens. The delta x's cancel, and now I can take my limit, meaning I can evaluate the limit. As delta x goes to 0, that guy goes away, and what am I left with? 2. So how about that? We know, and we can check this, we know that the function x squared plus 3, and let's just look at this graphically. So the function x squared plus 3, show you kind of a good little trick on your calculators now while we're doing this. So we want to make that x, ooh, no. Make that x squared plus 3, zoom 6, there's my function. If I go to the point, of course we know we can go trace 1, and there's the point, x equals 1, y equals 4. We want to know the slope there, right? So I can do this graphically. Whenever I have a graph, if I go second calc, I get all my graph tricks. Which one do you think I want? None of those look normal, but 6, doesn't that kind of look like changing y over changing x? Okay. Turns out that's another notation, dy dx, for what we're talking about. We're just starting to talk about, which is the derivative. So that means slope of the tangent. 6 does.
Then it just automatically makes
so I have to type in a value. If I type in the value 1 for x and I hit enter, it tells me that the slope is, you see that? Everybody see that?
So
The slope is 2.
we don't, all this stuff is just,
We can do it all in the calculator.
Well, okay, no, you can't though, because you're gonna be limited, because that told you the slope for one specific value, right? But isn't that, I mean, that's good, but wouldn't it be nice if we could instead come up with a function that predicted the slope for any value?
So that'd just be the 2 plus delta x in this case?
Well, it'd be, not exactly, it'd be a function in x, right? That would be nice.
can we just, test to see what x equals 3 would be or something like that?
Okay, so,
From
well,
that cross
Well,
reference?
what did we do here? What if we had done this problem a little differently? Okay, if we go back and look at the work that we did here, right, we said we have this function f of x equals x squared plus 3, and we're going to go to the point 1, x equals 1, which turns out to be y equals 4. Did I really need to pin it down to 1, though? I didn't, right? Why limit ourselves to a single value of x? What if I were to do this same process, but not specify a value of x? Can you kind of see how that might give us something really valuable? Our answer then would have been in terms of x instead of specifically in terms of that x value that I chose, right? So let's go back and repeat this process again. Same problem. But we want to be more general. Being general is always a good thing. Being general is going to allow us to come up with a universally applicable function or formula, right? So, let's try this. Okay, so let's go through the same process. We're going to start at the same place, right? The slope of the tangent line, which we're just going to call this time, I'm going to call it f prime of x. That's our notation for the derivative. Okay, and that equals the limit of, just like before, f of x plus delta x minus f of x over delta x. Delta x goes to 0. Okay, well, let's do the same stuff again, but this time we're not going to specify a point, right? So f of x plus delta x then is just going to be what? We said f of hand is just hand squared plus 3. So what's f of x plus delta x? So x plus delta x squared plus 3. Everybody agree? So green goes with green. So that is that, right? Okay, minus f of x is just x squared plus 3, right? Divided by delta x. Delta x goes to 0. Well, it's the same math, isn't it? I mean, we just did all this algebra. If I square out the binomial, x plus delta x, what do I get?
X squared,
X squared plus
2x delta x.
plus,
Delta x squared.
okay, plus 3 minus this quantity. So minus x squared minus 3, all divided by delta x. Look what happens. I can subtract away the x squareds, I can subtract away the 3's, and look what's left over. What can I do? I can factor out a delta x, can't I? Right, so we get the limit of delta x times what's left over?
2x plus delta x.
2x plus delta x over delta x. Delta x goes to 0, so I can cancel the delta x's to 1, the like factors, and evaluate my limit. So now I've got the limit of 2x plus delta x as delta x goes to 0, and so that term goes away, and I get my answer. It's 2x. Okay, that's huge. Think what that told us. So this is our original function. from that original function, we found that the derivative function, right? Maybe you didn't notice that. That's written in function notation, isn't it? The derivative function is 2x. So now, what's the what's the slope of the function at x equals 1? It's f prime of 1, which is 2. What's the slope of the function when x equals 100? 200. We got it anywhere. Look at that. See, that's way better than what we did with on the calculator. We just picked one point, but now we've got a function that calculates the slope of the curve anywhere. And when I use that terminology, the slope of the curve, that's new, right? We've never talked about curves having slopes before, right? But now we can talk about it that way, right? Because now we're able to find the slope of the tangent to the curve. That's the same thing as the slope of the curve, right? If I were to magnify the curve infinitely, centered on that point, the curve would become a line. Everybody agree? And so the line would be the tangent line. And so we really do know here that when we say now the slope of a line tangent to a curve, that's a lot to say. Once we've calculasified all this stuff like we just did, we can just say, yeah, the slope of the curve at this value of x is a value, right? Okay. You always can think about the slope of the curve as being just a little tangent line that's floating around the curve. As I drag the point along, the tangent's going to respond and change, right? That represents the actual slope of the curve. Okay? So what about
We have ones where we don't know what the equation is, and we have to figure it out.
what do you mean?
Like, for the graph right down the board, we have problems where you give us a graph and we have to figure out the equation, then we have to figure out the derivative for.
Yeah. Here's the kind of stuff that you're going to do in this problem set. So you're going to do stuff like, for example, whoops. I'm going to give you a function. I don't know, let's say square root of x. Is that one square root of x? That would work. That'd be a good one. Yeah, that'd be a good one.
Which all give us the function.
Square root of x. Now I want you to find what the derivative function is. And then maybe you could use that to do some other interesting stuff. Like let's find the equation of the line. That's a good one. There's the function. Find the equation of the line tangent to f of x at x equals 9. Okay?
Wouldn't you just be able to simply plug that in correctly?
Yeah, you could, but you won't be able to on the non-graphing calculator part of the test. And even then, yeah, you could. You could. Okay, but
Wait,
let's
you-
not. Let's do it analytically. What are the ingredients to find the equation of a line?
Slope.
Slope and, well, y-intercept or slope and a point, right? If we had a slope and a point, we come up with the equation of the line pretty easily, right? The point's easy. Point's a gimme. What's the point going to be? When x equals 9, we've got the point, what?
3.
9, 3. So that part's done. We just need to know what the slope is, though. That's what we couldn't get before, right? Well, now we can do it. Let's just try this once. So there's our function. We just want to find the derivative function and evaluate it at 9. That's what we're looking for. The slope we need, the slope of the tangent line, everybody agree is f prime of 9? Right? Okay? That's all we need. M equals f prime of 9, but we got to know what f prime is. We got to come up with that function, right? So where do we always start? What is, everybody together? What is it? The limit of
F
of
x plus delta x minus f of x.
Everybody's gotta come up with a song here.
X.
See?
That's
approaching
zero.
Okay, that's a tough one. That's a tough one. So our function is the square root of x. So these are easy functions to. We can evaluate the function at x plus delta x and x pretty easily. we just get the limit of, everybody agree that's just gonna be the square root of x plus delta x minus the square root of x over delta x. Delta x approaches 0. Now, what's our strategy for that's 0 over 0, right? What's our strategy for evaluating a limit like that? Conjugate. Okay, so we're gonna multiply top and bottom by conjugate at the top, right? Square root of x plus delta x plus square root of x. Right? And what's that give us on the top? So that's just a conjugate pattern, right? So we get difference of squares. First term squared is what?
X plus delta x. Middle term. So
Okay,
we get
minus, yeah, middle terms cancel, minus last term squared,
x.
okay, over that mess. Times the quantity okay, do I want to distribute the delta x on the bottom? No, don't want it. That's gonna mess things up, right? This will be a self-cleaning process when we take the limit. When we take the limit, all those ugly delta x's are gonna go away anyway, right? And that factor is gonna look a lot simpler. Okay, that factor on the bottom. So look on the on the top here, then we get x plus delta x minus x. Those go away, right? All I've got on the top is a delta x. Okay, so I could cancel vertically, and I just get 1 on the top then, right? Everything went away. But that's all I needed, because now I can evaluate my limit. So when I let delta x go to 0, I just end up, that term's gonna go away, right? This one's already canceled. That one goes to 0. And so I just get 1 over the square root of x plus the square root of x. It's the same thing as 2 square roots of x, right? So that's our derivative function.
So that.
So f prime of x equals 1 over 2 times the square root of x. So we wanted to evaluate it at 9 to find the slope of the curve at x equals 9, right? So then, what do we get? What's f prime of 9? 1 over 2 times 3, yeah, so 1/6. So we got it. There's our slope. We had the point 9,3. So if I want to come up with the equation of the line, I just know that, what do we get? We get y equals mx plus b, right? So y equals 1/6 x plus b. How do I solve for b?
You just plug in.
Yeah. Plug in a solution, x and y. So 9 goes in for x, 3 goes in for y. We get 3 equals 1/6 times 9 plus b. So b is going to be 3 minus 3/2.
Yeah.
So b equals 3/2. And then we get the line y equals 1/6 x plus 3/2. Well, let's just see if we got it right. Let's graph it, see if it looks good. So we have the function square root of x. Oh man, what was our line? Hang on one sec here. We got our line was 1/6 x.
Plus 3/2.
1/6 x. So make this quick. So 1
What is mess?
divided by
Oh, the top
6
one, yeah.
x plus 3/2
Yes.
plus 1.5 zoom 6. Looks pretty good, doesn't it?
Yeah.
Out there at 9. So there's the point of tangency right there.
Tangent I like to eat.
Are you kidding me?